Hey, welcome. This is a video introducing the Huffman decoder here. Okay. I have updated this website a little bit, so if you previously download this, please check the new one here. Okay. Um, let's look at the Huffman code, the Verilog entity here. So we have clock reset here. So for reset is 0, you do some initialization of the registers. If the reset is 1, you do your work here. Okay. Uh, Let me see. So for the Huffman decoding, basically we have the inputs is a sequence. Okay, the 16 bits of a code here. Okay, so this is a code with 16 bits, and we wanna iteratively check if the top n bits is a Huffman code here. For example, uh, we compare if 0 is a Huffman code, it turns out it's not. And we compare if 01 is a Huffman code. Okay, here, as you can see, here, 01 is a Huffman code here. Okay, so yeah, we just, this is what the code is. And how are we gonna know if one code is a Huffman code? We don't directly pass the Huffman code into this module. Instead, we pass in a Huff table here. Okay, so this is a Huff table. So what Huff table means is that Huff table shows you, okay, here, how many Huff table exist for each length here. So it has here, let me see. It has 16 levels here, and so basically there are 16 numbers in the Huff table, and each of the number is a 8-bit register. Okay, so the example here is Huff table. The first number is 0. That means there's no Huff code with length of 1 here. Okay. So this 2 means there are 2 Huff codes exist for length equals 2 here. Okay. They are 0, 0, and 0, 1. So the Huffman code always takes the smallest possible code here from left to right here. Okay. How we construct this Huffman tree, I think this is introduced in the lecture here, so I will not go over this again. Okay. So basically we can just construct this tree based on the Huff table here. But in our code, we don't actually construct the Huffman tree here. The way we do this is we keep track of a register called upper bound. Okay, I will introduce this later. And also, once we have the Huff code here, we want to convert this Huffman code to a corresponding symbol here. The symbols are fit into the design by this Huff symbol input here. Okay, so it has 256 symbol here, and each symbol is a 8-bit register. Okay, and for example, if the first 2-bit is a Huffman code 01, that means this is a second Huff code in this array. Okay, so the index here is 1, and we calculate the index and we just output the decoded symbol as feed it into the data here. Okay, so for this case, data is gonna be 2 here. Okay, And the length here is the length of the code you just decoded. So for example, for this case, for the first huffman table, we have length equals 2, and you raise the finish to 1 once you have detected one of these huffman code. Okay. So this is the input and output of this module, and I will show you how to do the decoding here. So for this Huffman tree, in each level it shows if there are any Huffman code in each level. So let's say take level 1 as an example. Okay, so in level 1 in total there are 4 code, right? 0, 0, 0, 1, 1, 0, and 1, 1. And if we take a look at the half table, we know that for level 1 here, there are only 2 code. There are only 2 half code here, okay? And the half code always comes from the left possible code. So the leftmost 2 code are Huffman code here. They are labeled as a red boxes here. And after these, we will have an upper bound. Okay. So basically that means upper bound is the largest possible Huffman code in each level. So if a code is less than this upper bound, that means it is a Huffman code. Otherwise, it is not a Huffman code. Okay, this is how you tell if a code is a Huffman code. And so if we want to do this part, we will iteratively compare the top n bits of this code if they are less than the upper bound. If they are less than the upper bound, that means we have a Huffman code. Otherwise, we will keep increase the number of bits here and compare to the next level. Okay. So we have some. I will not go over this again. I think they is self-explanatory. Yeah, so basically you iteratively update the upper bound for each level and compare the bits with the upper bound. And so let's go ahead. So let's see, what if you detect a Huffman code here? Let's say it's 0, 1 here. Okay, we calculate the difference between this code with its upper bound here. So in this case, we have, let me see if we have an example here. Okay, we don't have example for this, but we have example for the second half code here. Huffman code is 100. Okay, so we will compare, check the difference between this 100 with its upper bound 101 here. Okay, we have the difference. We calculate the difference. Okay, 1 0. The distance is just 1 here, right? And then the index. What is the index? So we have the code here. Okay, so the index is the index of this code in this array. Okay, so here the index starts from 0, right? So the index of this code should be 2 here. How do we calculate this? Is index equals the symbol count minus the difference. A symbol count, what is a symbol count? Symbol count is how many, it's just a cumulative summation of this Huffman code here. Okay, so for example, this is the level 2, right? So the symbol count will be 0 plus 2 plus 1 here. In total, there are three Huffman code from level 0 to level 2 here, 1, 2, 3, right? So the symbol count here, let me see. we have the symbol count the symbol count should be 3, and minus the difference we calculate in the previous step here. It's 1. So 3 minus 1, we have 2. This is the index of this Huffman code. All right. So finally, the symbol equals the half symbol with index of 2 here. This is the final symbol. Yeah, so this is just with index 2, and we will just output this 3. So here, this is the pseudocode, okay? So in total, we have the code with length of 16, right? So we only check the top 16 bit of this code. So if n is less than 16, let me see. We first take the top n bits of this code and update upper bound, update the symbol count, and compare it with new just updated upper bound here, right? And if we have this less than upper bound, we output the symbol. Otherwise, we increase n by one. Okay. So how do we stop this whole module? Is either we have a symbol, we will stop this module, and we have finish equals 1. Otherwise, if we already check the all 16 bits here, and so here we will have n equals 16 if we want to stop. Okay, so it goes to this else statement, and we check all the 16 bits, and we are not able to find Huffman code. We will just also raise the finish to 1 and output some all 1 is so this number will not be taken as a symbol since we don't have a Huffman code here. Okay. What else? I think we update something more. Okay, here. So sometimes you will need to take a specific number of bits from a long register in Verilog. And some of you may write it as this one. So if you have I as a register and the value of I is changing in your program, this is probably not going to work because you have a variable index. And for the variable index, in the software, it should be fine, but the synthesizer will be confused if we want to convert this into the hardware, right? So one way to work around it is we use the right shift. We right shift this by the number of bits we want, and finally we will have these 8 bits goes to bit 7 to bit 0, and then we just take the lower 8 bits of this signal, and finally we get the output. Okay. And also I run the test bench I provided the other day. It should work. Okay. So in this example, we have a half table matches here. And we have the symbol matches here. Okay. And we have the input of the code is like this. 6000. This is just this sequence. Okay. 6 is 0110, and the rest of them is all zeros. So it's just like this, right? So if you implement your design correctly, you will have the first symbol as 2, for second symbol as 3, and the rest of the symbols, they are all 2, right? So they are all 00 means 00 corresponds to, wait. Sorry, these should be all ones. I will update this later. The symbol should be 2, 3, and 1, 1, 1, 1, 1 here. Okay. So this is simulation. we can see we have the finish symbol here. And if the finish is 1, we will have the half data as output here, okay? The first symbol is 2, and then 3, and then 1, 1, 1, right? Yeah, now maybe it's easier to see. Okay, this is the finish, and this is the symbol. The first symbol is 02, second symbol is 03, and the rest of the symbol would be all 01 here, right? Yeah, you just compare these. And what else? And the length should always be correct. So the first, let me see. For the first code is the length is 2, right? And for this code, length is 3. For the rest of the code, lengths are all 2. Okay, so you will have the length 2, 3, and for the rest of the length, sorry, for the rest, it should be always 2, right? So 2, 3, and all the way, all the 2s. Okay, so this design is kind of hard, so I would recommend before your next lab sessions, at least make sure your test bench is working, or say your simulation is working. Okay. I guess that's it. Okay. Thank you.